this is another concept. I don't know if you have ever heard about the two-tailed and one-tailed test. So if you are looking at the difference, or you are comparing two things, okay, for population mean, we are interested to know if number one, if the population means are equal or not equal. Okay, if population means are equal or not equal. And then here we haven't taken in direction. Then the other test that we can do is to know if the population means is greater or less than a certain population mean. So if we want to test, like we have given an example of the population mean for everyone here, we said we hypothesized that the population mean for all of us here can be 40, right? Can be 40. Let me write here. So if we say the population mean is 40, the age population mean is 40 for everyone here. One researcher can want to know if the population mean is equal to 40. Okay, that is one way of testing. We want to know if the population mean is equal to 40. Okay, then in another way, someone may want to know, to just test if the population mean is less than 40. Okay, so if you are testing to know that we are just interested to know if the population mean is equal to 40. This is a two-tailed test. Okay, then if we are specific to say we want to know if the population mean is less than 40. Okay, this is one-tailed test. Okay, we have two-tailed here, and this is one-tailed test. So when we have a direction of the test, we are using one-tailed. Someone can want to know if the population mean is less than, or if the population mean is greater than a certain value. So that is, you have a direction which you want to test. But when you don't have a direction of you testing, which one you want, maybe either less or equal, you have a two-tailed test. Are we together on two-tailed and one-tailed test? Okay. So here we are interested to test the population mean. So our now hypothesis is going to say the population means um, the population mean is equal to the hypothesized population mean. Okay, or the population mean is not equal to the one that we hypothesized. So what I mean here, we have hypothesized that the average age for everyone here is 40. So we want to test if the average age is equal to 40. So we are going to say the average age that we can find after we calculate the actual average age is going to be equal to 40. That is the null hypothesis. Then the alternative hypothesis is going to say the average age, the actual average age that we are going to find after we calculate is not going to be equal to 40. It's not going to be 40. Okay? Are we together? Okay, great. Then, after we have stated the null hypothesis, we have to calculate now the test statistic. Okay, we need to calculate the test statistic. So like I was saying, when we are testing the null hypothesis, we are using a certain value to determine at which point can we reject and fail to reject the null hypothesis. So we are using, normally we use a p-value, but today we find the concept of the test statistics. So sometimes in the z-test and other tests that we are going to look at, we are going to be using the test statistics. Okay, so instead of finding the p-value, here we are finding the test statistic which you have to calculate. So now this test statistics is calculated using this formula. Okay, what is the difference, or what do these symbols denote? This one, x bar, and this one, what do they mean?
X bar is the sample mean, then mu is the hypothesized, it's the null hypothesis
Yeah,
of
so
the population.
yes, so this one is the hypothesized uh, population mean. So mu is the population mean, x bar is the sample mean, over, we're given the variance here, divided by the divided by n. Okay, so this is the formula. Remember, we are looking, the z-test is used when the variance is known. That's why we have the variance in our formula here. So this is now the formula that we are given. Okay, so once you test, once you calculate this test statistics, you have now to compare it with the z value, the z absolute value. Okay, you have to compare it with the z value. So the z value, okay, this is very important. The z value is given by, when we are looking at the two-tailed test, okay, at 5% standard error, the z value is 9, is 1.96. Okay, this is at 95% confidence level and 5% standard error. Okay, so the z value is 1.96. Okay, so this is now the critical value. It is called critical value, that we have to compare the test statistics which you calculate here, then you compare with the critical value. But for the critical value, you don't calculate, like I said. This one, you just have to know it, or you can get it from the table, depending on the alpha that you are given. So now alpha here, we give you that alpha is 5%. Okay, 5% standard error, which you can convert this one to 0.05. Okay, 0.05. Sorry, I'm not able to write properly. Yeah, so you compare your test statistics with the critical value. So now this critical value determines the rejection and acceptance region. The region in which you are going to reject the null hypothesis, and the region in which you are going to fail to reject the null hypothesis. So to easily understand this critical value, or to understand the rejection region, what you need to do is to make table like this one, not really a table, but yeah, a Cartesian plane like this one. Then you have this region here. So when you are looking at this critical value, the rejection and non-rejection, you are going to have this side, you're going to have negative 1.96. Okay, and this side you are going to have 1, sorry, Let go, yeah, 1.96. Okay, this side we are going to have 1.96. Then you are going to have these regions. You're going to have this region and this region here. Then you are going to have this other region at the middle. Okay, this region on the middle. Okay, then the statement says the greater or the bigger the absolute value of z, the one we calculate, the test statistics, the more possible to reject the null hypothesis. So this region in the red is the rejection region. Okay, these regions. So if we find a value, the test statistics, the one we calculate, if we find that it falls within these red regions, is greater than 1.96 or is less than negative 1.96, we are going to reject the null hypothesis. But if it falls within this green region, okay, if it is between negative 1.96 and negative 1.96, we are going to fail to reject the null hypothesis. Okay, is it clear on this one?
Come again, sir.
Okay, you have seen these regions that have made here.
Yes.
Yeah, so we have the test statistics, this one that we calculate using this formula. Okay, we look at the sample mean that is given minus the population mean, divided by the variance times, divide by the square root of the n, square root of n. Then we are going to find the answer. So if we find 2.1, okay, for instance, we find 2.1 after that, then this 2.1, you need to compare it with the critical value. Okay, so the critical value for the z test for two-tailed, okay, not that one, the z test for two-tailed is 1.96. That is the critical value. You are going to compare the test statistics that you find. Okay, so now this negative, this 1.96, it can be negative or positive. Okay, so now to understand at which point you are going to reject the null hypothesis, you should have something like this. So if the test statistic value that you calculate is greater than 1.96, okay, you reject the null hypothesis. Or if it is less than negative 1.96, you also reject the null hypothesis. But if it falls between these two values, you fail to reject the null hypothesis. Okay, so in this case, the example I've given, I said when you do maybe the test statistic calculation, you find 2.16. So you are going to come here and compare with 1.96, and this shows that 2.96 is somewhere here. Okay, 2.1, I mean, is somewhere here, is in the rejection region. So you are going to reject the null hypothesis, which says the population mean is equal to the hypothesized population mean. So you reject that one. You say the population means are not the same. Is it clear?
Yeah.
Okay, great. So that is the gist. Then we have one-tailed. I have explained on one-tailed. So one-tailed, we are interested to know if the population mean is greater or if the population mean is equal. So I've seen here the null hypothesis is going to say the population means are equal. Then the alternative hypothesis can say the population mean is greater than the hypothesized population mean. Or we can say the population mean is less than the hypothesized population mean. We are not just saying the population means are not equal, like in the two-tailed test. Here we have to specify either we want less or we want greater. Okay, then the formula or the steps are the same. What we just determine that you are going to have one value. Either you are comparing with less, which you go with the negative, or you are getting the positive side. So you are just using the one side of the rejection or non-rejection region. Okay. So we have this example. I want to look at this example first. We have this example which says researchers are interested in the mean age of a certain population. So the data available to the researchers are the age of the 10 individuals. So we mark this one. We have 10 individuals drawn from a population. From this sample, the average age is 27. Okay. So from this sample of 10 people, the average age is 27. Okay. Of a known variance, which is 20. Then they say test the hypothesis that the average age is 30 with a 5% significance level, which is the probability of making type 1 error. So this question is similar to what the example we gave yesterday. Yesterday we just said that the hypothesized value was 40, but here we are given 30. So it's more like from all of us here we say the population mean or our average age is 40. Then we get 10 of us. We get 10 of us and calculate the what? The average age. So when we get 10 from us, we calculate the average age is giving us 20. And the variance, we're getting the variance of 20 as well. So now we need to determine if the population mean is really 40. Here in case we are using 30. Is the question clear? Most important is to understand the question. Anyone who is lost on this question?
I think I request you go through again.
Okay. Anyone who can read the question for us? I want a different voice to read.
Researchers are interested in the mean age of a certain population. The data available to the researchers are the ages of 10 individuals drawn from a population. From this sample, the average age is 27, coming from population of known variance of 20. test hypothesis that the average age is 30 with 5% significance level, probability of making a type 1 error.
Okay, anyone to interpret, to explain this question?
Yes, what the question is saying that there are 10 people that have been sampled from the population to do the test on them. And once they gave us their ages, it was discovered that the average age mean is 27. Then the variance from the same population was 20. So they are telling us at the hypothesis average age is 30 with the significance level of 5%, which is 0.05. So they're telling us to prove whether it's a type 1 error or it's not. That's what I've got from this question.
Okay, great. Yeah, so they are telling us to prove or to test if this sample, which has the 27 average age, is coming from a population with the average age of what? 30. Okay. Yeah. So they are telling us to prove or to test if this sample is coming from this population with the average age of 30. So that's what we need to prove. Okay. So first, you are going to state the null hypothesis. Okay. So the null hypothesis will say the average age or the population means are equal. That means the population mean where this sample is coming from is equal to 30. Okay. Then the alternative hypothesis is going to say the population mean where this sample is coming from is not equal to 40, to 30 I mean. Is it clear? Okay. Please don't remain behind. If you are not clear, ask. So now we go to use our formula. We have all the values here. We go to use our formula, which is on top here. Yeah, which is this one. So we have x. What is x?
27.
X bar 27. Yes. Hypothesized mean
30.
this 7. This is 7. Look, it looks like 22. Okay. Hypothesized mean we say is 30. Okay. Then the variance 20. Then n.
10.
Okay, 10. Yeah, this is the variance. Then this side is 20. Yeah, so actually, when we see this one is a standard deviation. Okay, this symbol is for the standard deviation. Now we know that the standard deviation is the square root of the what? The variance, right? Do we still remember those calculations we're doing? Yeah, after you calculate the variance, then to find the standard deviation, you just square root the the variance. So now let's do the calculation here. So we are going to have 27 minus 30. Okay, divide by this one. This one is the variance. Okay, so to find the standard deviation, you have to square root what? 20. Are we together? This in the formula is the standard deviation, but what we are given is the variance. So to find the variance, the standard deviation, you have to square root the variance. So that is going to be, we just make one square root because we are square rooting both the number and the variance. So it's going to be 20. Square root of 20 divided by what? 10. So we can do the subtraction here. 27 minus 30, negative 3. What is the square root of 20? What's the square root of 2 point?
4.47.
Or 4.4. 4.47. Then the square root of 10,
3.16.
3.16. Okay, so this one is going to be negative 3. Let's divide by 4.47 divide by 3. You say 3.16.
Yes.
It gives us what?
1.41.
1.41. Now we can divide. Negative 3 divided by 1.41. What is the answer?
Minus 2.13.
Minus 2, negative 2.13, right?
Yes.
Okay. So now, remember, our now hypothesis is saying the population mean where this sample is coming from is equal to what? Equal to what? 30, right?
30.
Yes. Then our alternative hypothesis is going to say this sample is not coming from the population mean, is not equal to 40, or we can simply say the population mean is not equal to 30. Okay? Yeah, so we have find the test statistics. Hello?
Is it not a one sample? One tailed?
Yes. No, this one we are using two-tailed. We can use two-tailed. So we find one value. Actually, no, you are right, because this is now the absolute value. Okay? In the two-tailed, we find the absolute value. So this value that we have found, when we say absolute value, that means it doesn't have a sign, right? We can remove the sign. So it's gonna be 2.13. So it's an absolute value for the two-tailed. Yeah. So now we look at this value that we have found, which is negative 2.13 or 2.13. Okay. Then compare with the critical value for the Z test. The critical value for the Z test, where we have 1.96 a negative 1.96. Okay. So where do we place the value that we have found? We have the rejection region and we have the non-rejection region. Where does it fall? In the rejection region or in the non-rejection region?
Rejection region.
So it falls in the rejection region. So it can fall within this rejection region. So we have tested this hypothesis and we say the population where this sample is coming from is not equal to 30. The average age where this sample is coming from is not equal to 30. Okay. Any question? Any question on this one, please? Yeah, so that's what we were testing. And then I want us to look at one-sided. So now, suppose instead of asking if they could conclude that the population mean is not equal to 30, the researchers are asking whether they can conclude that the population mean is less than 30. Okay? The researchers are asking if they can conclude that the population mean is less than 30. So now this is one-tailed. They want to know if the population mean is less than 30. Then the null hypothesis now is going to say the population mean is greater or equal to 30. It will be the opposite of what we are looking for. Okay? Then the alternative hypothesis, it will be direct to what we are looking for. So it will be the population mean is less than 30. Okay? Then we do now the calculations. Where is my case? Oh. Okay, I'm trying to move the screen. We do the calculation using the same formula. And here we are interested on one side. Okay, so this value that we have found, after we have calculated, we found this value, which is the same as the one that we have found. So we go to the rejection region. Okay, so this we are interested in knowing if the population mean is less than 30. So we look at the critical value for the one-tailed test. So the one-tailed test has a different uh, critical value. Okay, we are no longer using 1.96. 1.96 is for two-tailed. For one-tailed, the critical value is 1.645. Okay, this is the critical value. So this value that we found, we have to compare it with 1.645. Okay, so when we look at this value, you draw the same line. So we can have negative 1.96 and positive 1. We can have negative 1.645 and positive 1.645. So we look at this value that we have found. Does it fall within the rejection region or the non-rejection region?
Rejection.
Yeah, so it is in the it is in the rejection region. So we are able to reject the null hypothesis, and we conclude that the population mean is smaller than 30. Okay, that which we are looking at. We reject the null hypothesis, which says the population mean is greater or equal to 30, and we conclude that the population mean where this sample is coming from is less than 30. That is the meaning. Any questions so far? Yes, please.
Yes, sir. I just wanted to find out, is 1.645 standard?
Yeah, it's standard. This one is standard. It's standard. As long as you're using a 5% confidence interval or significance level. 5% significance level and 95% confidence interval. So the critical value for one-tailed, it will always be 1.645. Okay. For two-tailed, it's going to be 1.96. Always. It doesn't change. Hope now it's clear. Or there are people who want to join this side.
What if you're using the 99 and 1%?
There is no 1%. I don't know. Is there 1%? But mostly this is what we use. And when you are using that, but I doubt, but there is a table. Yeah, so you don't have to write this one. You can Google there is a table. So you are going to find these values are given. I'm sure it is there. It is there in the table. These values are given. Okay? You are going to find the value this one. The 0.5, 0.25. So why here it becomes, for the two-tailed, we have this 0.5. But now when you are looking at the two-tailed, you divide by 2. And it will give you 0. 0.025, right?
Yes.
So when you go to the standard table, where the z value is 0.025, at the absolute value, it will be 1.96. And when the z value is 0.05, it will give you this one. It will give you 1.65. So it's there on the table. So if you are given a different confidence interval, then you have to refer to the table. You cannot memorize these ones. Unless these that are standard. These two are standard. For 5% significance level is standard. Even if you don't have to refer to the table, you just have to know that for two-tailed is 1.96 and for one-tailed is 1.645. Yeah. Okay. So now we can test this same hypothesis using the 100% confidence interval. Okay. we can test it using 100% confidence interval. So this is another way of testing the null hypothesis. And now this one is given by this formula, okay, which is x bar plus or minus the z absolute value for two-tailed, okay, times the standard error, okay, times the standard error, where the standard error is given as this one, the variance, or variance divided by total number of participants in that study. Then the z value for two-tailed, we know that is 1.96 from the standard normal table at 5% significance level. Okay, so now if we are to use this formula, you find that here you have to put x bar is 27, which they have included here, plus the z value, this one, which is 1.96, okay, multiplied by the square root of 20 divided by 10, okay. So when they do that, when you multiply this one, it gives you 2.774, okay, 2.7714. Then you add or subtract. So when you add 27 plus 2.7714 gives you what? Hello? 29. Yes, 0.774. When you subtract, it gives you what? 27 minus 27714. So it gives you these values here. Where is okay, see, it gives you these values here. Okay, so when we subtract, we are going to have 24.2286. When we add, we are going to have 29.7714. So you know what this means? Do you know what this means?
No.
Yeah, yeah. So this one, yes? Someone want to try?
Yes, it's the range.
Yeah.
So meaning the mean is within the range of 24.2286 to 29.7714.
Yes. So the range for the age where this sample is coming from, it ranges from, it's in this range, it falls within 24.22 to 29.77. That is the range. So it is not 30 like we have already rejected it, but it is found within this range. Okay, so the what you have to know is that, oh sorry, it has gone somewhere. Yeah, so it says since interval does not include 30, so we have seen between 24 and 29, 30 is not there. Therefore, population mean is not equal to 30. And we reject the null hypothesis, which says the population mean is equal to what? to 30. Okay? So in general, when testing a null hypothesis by the means of a two-sided confidence interval, we reject the null hypothesis at if the hypothesized parameter is not contained within the 100% confidence interval. So if the hypothesized mean is not contained, like we have seen in our case, we have 24 to 20 what? To 29. I've written something else. 24 to 29. So the hypothesized parameter, which is 30, is not contained within this range. And since it's not contained, we are going to do what? To reject the null hypothesis. Then, if the hypothesized parameter is contained within the interval, the null hypothesis cannot be rejected. So for instance, if we have found maybe 29 and 31, this means that 30 is in between here, is enclosed. So when it's enclosed, we cannot reject the null hypothesis. Are we together? Any question? Any question, please? Let's ask. Let's ask.
Good morning, sir.
Good morning. Thanks.
For me, it's not necessarily a question. You know, I felt very bad. I overslept and I really wanted this. I don't know whether there's a recording. So if I was to ask here, I won't even know what I'm asking, but I've understood what you've explained. But now where you began from, I don't know whether you're going to do a bit of a summary at the end.
Okay, great. Today we are lucky. My phone is okay, so I'm recording. Don't worry.
Oh, thank you.
Yeah, I will share the recording just after the class.
Okay, thank you.
Yes. Any other question? Any other concern? Okay, yeah. So that's for the one sample. So tomorrow when we come, we'll look at the two population means. How can we test the statistics for the two population means? So just maybe we can go through a bit. Yeah, so we have two population means, and the steps are the same. The first step, you state the hypothesis. So for two population means, you are going to say the two population mean, that is population 1 and population 2, are equal for two-tailed. Or the alternative hypothesis, you are going to say the two population means are not equal. Okay? Then for one-tailed test, the upper tailed, that is now if you want to know that the population mean, one population mean is greater than the other, that is upper tail test. You want to know if one population mean is greater than the other population mean. So the null hypothesis is going to be the opposite. It's going to say population mean 1 is less or equal to population mean 2. Then the alternative hypothesis is going to say the population mean 1 is greater than the population mean 2. Same applies to the lower tail test, where you are looking at, you want to know if population mean is less than the other population. So here you say the Population mean 1 is greater or equal to population mean 2, while the alternative hypothesis is going to say population mean 1 is less than population mean 2. Okay? Then after you have stated these now hypotheses, this is just the summary of this. So if we say population mean is equal, that means if you subtract these two population means, they'll give you what? They'll give you 0, right? If they are equal, that's what it means. But if they are not equal, when you subtract, the answer won't be what? Won't be 0. So these are just the summary of what these are the things are saying. So now you have to first calculate the test statistics. If the variance is known, okay, population standard deviation are known, which is deviation 1 and deviation 2. Then the test statistics is going to be given by this formula. Okay, the test statistics is going to be given by this formula. So this is the formula to calculate the test statistics, where we say x bar 1 minus x bar 2, okay, minus x bar, okay, population mean 1 minus population mean 2 over, okay, you divide the variance for the first population with the total number of the people plus the variance for the second population divided by the total number of people for the second population. Okay, yeah, so this is the formula that we use for the two sample, for the two population mean. Are we together on the formula, or have we written the formula? So the question that we are going to look at tomorrow when we come, we'll look at this question. We'll explain this later. So, anyone to read this question?
Researchers wish to know if the data they have collected provided sufficient evidence to indicate a difference in mean serum uric acid levels between normal individuals and individuals with Down syndrome. The data consist of serum uric acid readings on 12 individuals with Down syndrome and 15 normal individuals. The means are X bar 1 equal to 4.5 milligrams per 100 mil, and mean bar 2 equal to 3.4 milligram per 100 mil. Assuming that data constitute two independent samples, each drawn from a normally distributed population with a variance equal to 1 for the Down syndrome population and 1.5 for the normal population.
Yes, so now we need to test if these have different means. Anyone who can explain this question, who have understood? Okay, so these two, we have two samples, right? Two population. We have a population of individual with what? With Down syndrome, right? And the normal individuals. So the question, we want to calculate if these people have different level of serum uric acid. Okay, if uric acid level is different in these two groups of people. So that's what we are going to do when we come tomorrow. Hope we have understood the question.
Yes, sir.
Yes, so that's what we are going to do. So we are going to know if they have different uric acid levels. So we'll do that. For now, I think we end here if there is no question.
Sir, you can go up a bit. There's something that I want to ask there.
I continue.
Yes, you continue. I'll let you. Somebody has to scratch. Yes, just there. Yes.
Okay.
So, on the possible hypothesis, there on what do you mean when you say the upper tail test and the lower tail test? I understand on the two tail and one tail.
Actually, now these are one tail test. These two. So you can be interested to know if the population mean is greater than the other population mean. So that is upper. You want to know that like those individuals with the Down syndrome, you want to know if their uric acid is greater than the normal individual. That is upper test. Then if you want to know if they have low uric acid than the normal individual, that is the lower test.
Okay.
Yes. All right, thank you. If no more question, unless there is a question, please feel free. We still have 5 minutes. If you have question.
Miss, the request is not a question.
Okay.
Yes, I think Miss, basically I think I'm behind. I didn't get you clearly. I'm requesting tomorrow you can run us through what we've read today.
All right, come early tomorrow. We'll start at 05 exactly, so that we will try that first 5 minutes. For all of you who have not understood, join early tomorrow. Start at 05 exactly till you try that 5 minutes that we always lose in the morning.
Thank you.
You're most Thank you. You're welcome.
Thank you so much.
All right, work well, colleagues.
Okay. Work well too.
Thank you.